Hello there, kiddos. Now we are on to our types of immunity. If you weren't in class, do make sure that you watch this little Amoeba Sisters introduction to immunity video. It's a great little video that just introduces us to the types of immunity that we have and what the difference is between some of the agents of immunity, etc. And just in terms of terminology here going forward, the term pathogen is an umbrella term for any agent that can cause illness or make us sick and spurn an immune system response. So a pathogen is anything that can cause disease. So that could be bacteria, it could be worm, it could be a fungus, it could be a virus, so anything like that. Anything that has the ability to make us sick. Now, don't get that confused with an allergen. When a person has an allergic reaction, that's an inappropriate immune system response to something that's actually harmless, not a pathogen. Okay, so for example, if somebody is allergic to shellfish, shellfish is not a disease-causing agent, but when a person has so it's not a pathogen, but when a person has an allergic response or allergic event in response to eating or shellfish, then that means that the immune system is reacting inappropriately to something that is actually harmless. Okay, so let's take a look here. So when we talk about immunity, the first term that we'll take a look at is active. Now, active immunity basically means that antibodies are going to be produced by your own immune system. Okay, so anytime your immune system is engaged in making antibodies to fight off infection, that is called active immunity. When we talk about passive immunity, this is much less common because this is immunity that is received from another organism. The most common example of passive immunity is when a mammal, okay, starts breastfeeding. So if we look at a human, when a baby is born and a baby starts to breastfeed, the initial substance that comes out is called colostrum, and that's almost like a jelly type substance, but it is full of the mother's antibodies. And so that's why it's really important, if possible, that the baby breastfeed long enough to get this injection of antibodies from the colostrum, which is kind of the precursor of before the milk actually starts to come through. So that would be an example of passive immunity because the baby is actually getting antibodies from the mother and getting the blueprint for those antibodies from the mother. Now, when we look at natural immunity, one thing that's important to think about when you think of natural immunity is this is also active. Okay, so that means that we're not getting antibodies from another organism. We are producing the antibodies ourselves. But natural means that this is because we have been exposed to a pathogen. Okay, so when you catch a cold, when you catch a flu bug, anything like that, you catch chicken pox, anything like that, that is considered active immunity because your body is going to make antibodies in response to that pathogen, but it wasn't due to a vaccine. Okay, so natural immunity means you actually came into contact with the legitimate living pathogen, and that pathogen made you sick, and your immune system responded by making antibodies. So that's the active part there. So when we talk about artificial immunity is also active because your body is still reacting by making antibodies. So when someone gets a vaccine, okay, so when we've all heard in the news a ton about vaccines lately with COVID and everything, but when a person is inoculated or vaccinated, that is considered artificial immunity because your body hasn't actually come into contact with the real live pathogen. So typically speaking, when someone is vaccinated, the virus in the case of COVID or whatever is not, and it depends which type of COVID vaccine you got, because of course there's the mRNA ones and etc. But when we're talking about the traditional vaccines, okay, so vaccines that you would get for chicken pox and mumps and measles and those kinds of things, the pathogen is not actually live, okay? So it can be fragments of the proteins that are associated with that pathogen. But in any case, when your body gets a vaccine, that's considered artificial immunity because it's not natural exposure, but it's considered active because your body, in response to coming into contact with a foreign protein, is going to make antibodies. Now, the reason why some people feel sick after they get these vaccines is because if your immune system is working properly, then that means that you can react to having this active immunity kind of taking place. So sometimes people will feel sluggish, they'll feel tired, maybe they'll have a little bit of a fever, and that is all part and parcel of your immune system creating a response to the vaccine and helping you produce antibodies for protection. Now, on rare occasion, sometimes there will be live vaccines, and an example I can think of for that is if you get a flu vaccine, if you get the one that is the injection, then that is typically not a live vaccine, but sometimes for younger kids, but especially if they're scared of vaccines or whatever, you have like the nasal spray one, and that one is actually considered, it's a very, very small dose of the actual flu virus. Oh, we get to see it again. I don't know why this is crazy animations. Anyway, I should get on that. So when we are looking at the human defense system, there's kind of two categories that we take a look at. We take a look at the first line of defense, and then we take a look at the second line of defense. So one thing to remember with the first line of defense is that this is the first line. This is what prevents you from getting sick in the first place, because it prevents the pathogens from getting into your system. Okay, so I want you to think of your skin. Your skin is an excellent barrier to pathogens, okay? So unless there's a wound or a cut or whatever, it's very difficult for pathogens actually to get through all those layers of your skin. In addition to that, your skin produces oil, and a lot of pathogens like bacteria do not like oil, so they don't stick around on the skin for very long. If you think of like your nasal cavity, your first line of defense also includes mucus. So when you are breathing, any pathogens that go into your nasal passages, a lot of those pathogens are caught by that mucus, and you like can sneeze them out, or if they get into your respiratory system, the mucus traps them and cough them out before they actually make you sick. Okay, so anything that helps us not get sick in the first place is considered to be the first line of defense. Other things that you can think of is eyelashes, eyebrows, right? Those kind of trap dust particles and things before they can get into your eye. Tears, you might notice when you're sick, you especially if a cold or something like that, your eyes kind of get teary and leaky. And again, that is your body's immune system response to try and flush out the pathogens, okay? So first line of defense, or if you get something in your eye and it waters, first line of defense is before your white blood cells get involved. So there's other things as well. So if you think of like stomach oil or stomach acids rather, we talked about hydrochloric acid being very inhospitable to bacteria, for example. So that helps us control a lot of pathogens before they can actually make us sick as well. The second line of defense is when that first line of defense fails. Okay, so we've all been sick before. We've all had colds or flu or whatever. And when your first line of defense is not capable of keeping out the pathogens, so the pathogens actually get into your system and make you sick, that's where our second line of defense actually comes into play. And the second line of defense involves all those different kinds of leukocytes or white blood cells that we talked about previously. So if we take a look at our little graphics here, we have a couple of different types of white blood cells that we'll talk about in a little more detail in later slides. But this guy here is one of our monocytes. This is a macrophage, and a macrophage is involved in, as you can see in the graphic here, almost looks like a little spidery kind of thing. And what it does is it engulfs and destroys a pathogen, okay, and we call that phagocytosis. Maybe you remember that from Science 10, maybe not. But anyway, so it kind of puts those big kind of macrophage arms out, and it brings the pathogen in, and it destroys it and renders it incapable of reproducing. Now, one thing to know about those white blood cells that we call the macrophages is they are non-specific. And what that means is a macrophage can go after any type of pathogens. So it might ingest a bacterium, it might ingest a parasite, it might ingest fungi. Okay, so it can ingest many different types of bacteria, or many different types of pathogens rather, to keep us healthy. Now on our next slide here, these are our lymphocytes. And if you remember, we kind of talked about on previous slides, our lymphocytes are our B and our T cells. So you can see they look different, right? Our B and our T cells are involved in specific defense. So this means antibody production, right? And if we take a look at our third graphic here, you can see that there's those characteristic Y-shaped antibodies. And we call this specific defense when antibodies are involved, because antibodies that are produced by our second line of defense, okay, by those B cells, T cells, those antibodies are involved in protecting us against a very specific invader. Okay, so not any invader, a specific invader. So you have many, many different kinds of antibodies lurking in your immune system right now. And they have all been created in response to a very specific pathogen, not just any pathogen. So that's the difference between non-specific with our macrophages and specific with our lymphocytes. So the chief function of any type of white blood cell, whether it's the macrophage or the lymphocytes or whatever, is to defend the body against viruses, bacteria, and other foreign particles to prevent us from getting seriously ill. Now, white blood cells, for the most part, are not in the circulatory system specifically. The white blood cells actually kind of float around in the interstitial fluid and in that lymphatic system, in that lymph fluid. So remember those lymph vessels we talked about, and we talked about how inside the lymphatic vessels, we call that fluid lymph. And so we'll have those white blood cells moving around through our lymphatic system, traveling through that lymph as well. And remember, interstitial fluid, remember that guy? That's the same as extracellular fluid, okay? So that's kind of one important thing to remember is we don't have our white blood cells floating around in our circulatory system vessels specifically. They spend most of their time in that extracellular fluid, bathing the cells, looking for pathogens, and in the lymphatic system, in that lymph floating around through our lymphatic system, which runs parallel, of course, and is intertwined with our circulatory system. So, we've all heard of pus before, so even if you think of like a pimple and you get like a little whitehead pimple or a little pussy pimple, basically those are dead white blood cells. So anytime there's pus, that's always a sign of infection is present, and white blood cells are dying in the course of fighting off those infections, okay? So anytime someone has a pimple or a wound or whatever and it gets like pussy and kind of nasty, that's because the immune system is working to fight off that pathogen, and there's a lot of casualties in the terms of white blood cells. So that's what makes up that pus. So of course, if it's a pimple, that's one thing, but if it's like a wound and it becomes all pussy and nasty, then sometimes antibiotics may be required to address a potential bacterial infection. So in terms of where white blood cells are produced, we kind of talked about this previously when we talked about cell components, but keep in mind that white blood cells are primarily made in the bone marrow, just like red blood cells, and they are also formed in the spleen, which remember is one of our organs of our lymphatic system that we talked about before. Oh, and again, I have to address that. Okay, so when we talk about our different types of attack, we kind of talked about this a little bit already. We talked about our non-specific phagocytic attack, and then we talked about our antibody-mediated attack, which is our specific attack. So if we look at our little chart here, this would be an example of a macrophage. So monocytes is kind of an umbrella term, and the one that we have to be familiar with is macrophages. Now, macrophages typically live about 3 days or so, so they don't have a really long shelf life, but what they do is they wander around through our extracellular fluid, through our lymphatic system, and anytime they encounter a pathogen, whether it's a bacteria or it's like I said, a parasite or whatever, they will do that phagocytic attack, right, where they engulf and destroy. So keep in mind that when we talk about those macrophages, that is non-specific attack because they have the ability to attack any foreign agent that has the potential to make us sick. Now, when we look at our next two categories here, our lymphocytes, our B cells and our T cells, in terms of lifespan, they can live for many, many, many years, lurking in our bone marrow, kind of waiting for a secondary infection. And they are involved, of course, in antibody response. So you'll notice there's a bit of a difference here because it says the B lymphocytes or the B cells are antibody production. And what that means is that the B cells make antibodies specifically. The T cells are involved in assisting the B cells in making those antibodies because they give information to the B cells about what kind of antibody to make. But it is the B cells specifically that are responsible for creating antibodies. So when we talk about what the lymphocytes do, that's our antibody-mediated attack. So anytime antibodies are involved, excuse me, we call that specific defense, because remember what we said, antibodies are capable of addressing one pathogen only. So when we look at the shape of antibodies, and I know we did talk about this before when we were talking about macromolecules, I think, actually. So we have this constant region in our Y-shaped antibodies. So all antibodies have this constant kind of stem on the Y that is the same. But then up here, where we have the two kind of ends of the Y shape, we have a specific region. And this region is actually shaped for a specific pathogen's protein. Okay, so it's made to attach to a specific pathogen and attack a specific pathogen, not any pathogen. Okay, so when you get a vaccine, okay, so for example, when you got a vaccine for chickenpox, and we call that varicella is the proper name, when you got vaccinated for chickenpox, your body made antibodies that were specific to the varicella pathogen only. Okay, so your antibodies that your body made for chickenpox are not going to work against mumps, and they're not going to work against the flu, and they're not going to work against the common cold. Okay, so that's why we call the antibody-mediated attack specific. Okay, so we have the constant region, and then we have the variable region. So when we talk about the attack process, as we already said, phagocytic attack is non-specific. So if we look at our graphic here we have our phagocyte, or our macrophage is an example of a phagocyte. And notice what the macrophage does here. It engulfs and destroys. Okay, so again, this is non-specific. So this in the graphic says bacteria, but it could be a virus, could be a parasite, could be a fungi. Okay, any pathogen, our phagocytes are capable of engulfing and destroying, okay, through phagocytosis. So one thing to remember about the phagocytic attack is the macrophages are always engaged first, okay, because we don't actually make antibodies until our macrophages are overpowered. So if the pathogen is really, really strong, and you have a super high viral load or bacterial load, then sometimes the macrophages can't do what they are supposed to do in terms of keeping on top of that infection. And when that happens, then the lymphocytes get involved. Okay, so if the macrophages are overwhelmed, then the B and the T cells get involved, and we start to do that antibody-mediated attack. Now, the other thing to remember about phagocytic attack is this is happening all the time. So for example, in your lungs, you have macrophages that are in there in the extracellular fluid, floating around. If you inhale something that is damaging to you, like you inhaled some spores or something from fungus, then those macrophages are going to find those pathogens and they're going to engulf and destroy them. So this is happening all the time. This is part of your body just working to keep you healthy. However, when the macrophages are overwhelmed by a specific pathogen or more than one pathogen, then our B and our T cells are going to get involved in the attack. So notice that this process is actually IB, okay? So this kind of 1 through 4 process, that is specifically IB. So what does the macrophage do? It basically puts a coating on the invader so that the invader can't move. It dissolves the membrane of the bacteria or whatever it is and kills it. And then it attracts the macrophages, which then engulfs and destroys. So when we talk about antibody-mediated attack, this is your long-term defense against infection, okay? So because your body has the ability to store antibodies long-term to protect you against secondary infection or repeat infections of the same type. So this is your body's ability to establish antibodies to fight against foreign pathogens. So in terms of terminology, and this will be important when we move forward into blood types as well, antigen and antibody are two important terms, and it's easy to get them confused because they kind of have the same prefix, right? So one thing I want you to remember about antigen is this is the specific protein that identifies a type of cell. Antibody is the Y-shaped protein made that is specific to an antigen. So remember we talked about on the previous slide, if we have like the chickenpox virus, The protein on a chickenpox virus is a very specific antigen. And then your body, in response to either catching chickenpox or getting a vaccine against chickenpox, is going to make an antibody specific to that protein so that it can attach itself with that variable region to that particular pathogen and help destroy it. So one thing to take a look at as well is kind of the role in the lymphatic system again. So we already talked about the lymphatic system a little bit, but we're just going to revisit that in a little more detail in terms of how it applies to our white blood cell production. So I think I remembered saying in class before when we talked about the lymphatic system that in your chest cavity, and you can see where it is here, it's kind of nestled between your lungs here, you have an organ called the thymus. And the thymus is very, very active in infants and toddlers. Okay, notice it has a mass of about 70 grams, but once puberty is reached and then continuing into adulthood, it atrophies, and by the time a person is elderly, it actually is just kind of a very small lump of fatty tissue. So notice that in adulthood, it goes like all the way down to 3 grams. And the reason for that is because your thymus is very, very active when you're little because it's actually producing different types of lymphocytes. And then once those lymphocytes have been produced and your body has the blueprint, so to speak, for those lymphocytes, the thymus no longer has to produce them, okay? So in terms of production, I want you to think of thymus, starts with a T, and that's what the thymus gland produces, okay? So it produces those T cells or those T lymphocytes. Now, if we talk about lymph nodes specifically, we have a couple graphics here. So here's our lymph node, and this is actually a micrograph of a lymph node, which is kind of cool. And this one shows like an actual swollen lymph node. And notice all the blood vessels here, etc. Okay, so what are lymph nodes? Well, remember we talked about lymph nodes being distributed. They're in your neck, they're in your collarbones, they're in your abdomen, your groin, etc., and armpits, etc. And lymph nodes are responsible for a number of different things. So lymph, remember, is that fluid that passes through the lymph vessels. And of course, lymphocytes are our B and our T cells. So lymph and lymphocytes travel through lymph vessels and into lymph nodes where the lymphocytes actually destroy the harmful substances. So if we look at our little graphic over here, you can see that we have this super high concentration, densely packed. We have B cells and T cells in those little lymph nodes. And when the lymph travels into our lymph nodes, okay, coming through our lymphatic system, and it goes into our lymph nodes. A lot of times there's pathogens in there, and so what will happen is those lymph nodes will activate the B cells and T cells in destroying those harmful substances. And that's why when someone is sick, they actually get that swollen lymph node or swollen lymph nodes like it shows in the picture here, because there's a proliferation of white blood cell production and activity in there. Okay, so it's not uncommon to have that swelling when someone is actually fighting off an infection or just after they fought off an infection. But it should go down and go back to normal after the person is well again. And just keep in mind that the lymph fluid, after it is kind of cleaned up, it's going to be routed back into the subclavian veins and then eventually to the superior vena cava. So when we talk about T cells, we're going to talk about the helper T cells first. So remember, there are several different categories of B cells and T cells. So if we were going to define what our helper T cells do, our helper T cells are the information collectors and or the translator cells. So what do? They collect. So first of all, when you're sick, an antibody-mediated attack needs to begin. What the helper Ts do is they collect antigen information from the macrophages. So remember what the macrophages do. They engulf, they destroy, and what they do is they isolate the antigen, they isolate the protein. And then what they do is they give that protein to the helper T cells. So that's the first thing. So the helper T cells collect the antigen or the pathogen information, protein information from the macrophages. Then what they do is they confirm it. So you can kind of think of the helper T cells as like they're the proofreaders or the confirmers. So what they do is they assess the antigen shape, they mingle with the invader, and they kind of proofread it and establish, okay, this is what we're dealing with here. This is the antigen, this is the protein, okay, which is different from other proteins. Then the helper T cells, and this is why they're called the helper ones for sure, is they actually deliver, okay, the antigen information to the B cells in the bone marrow. Because remember, T cells don't make antibodies directly, but they are crucial in giving that protein information of the pathogen to the B cells so the B cells can make the appropriate antibodies. And the other thing that they do, which is kind of cool, is they inform killer T cells, also known as cytotoxic T cells. They inform them to attack once antibodies have been attached to the invader's antigens. Okay, so get the antigen information from the macrophage, confirm it, proofread it, pass it on to the B cells so the B cells can make antibodies. Once the B cells have made antibodies and they've attached themselves to the pathogen and the pathogen is immobilized, then the helper T's call the killer T's, and the killer T's come and they destroy the pathogens. So plasma B cells are sometimes just called B cells, okay? But the proper full term to distinguish them from memory B cells, for example, is plasma B cells, all right? So what do? They receive, so we talked about this on the previous slide, they receive the antigen information from the helper T's and they start to make those specific antibodies that we talked about already, right? So specific to the protein on that pathogen. They produce antibodies specific to certain pathogens, all B cells, and all the cells that will be made after that from that original B cell blueprint are going to make only one type of antibody, and we call this clonal selection. So there's no such thing as a B cell, once it has that blueprint from a helper T of the antigen of the pathogen, there's no such thing as it switching and, oh, I'm going to make different antibodies now. Once a B cell is programmed to make a certain antibody, that is the only antibody it will ever make, and any B cell that derives from that one will make the same antibodies as well. So there's no like changing your mind and being like, oh, I want to make this antibody instead. Okay, once it's established, it's done. And then what they do is, and this is a very important piece which we haven't discussed yet, is they will pass on that antigen information to the memory B cells. Okay, and the memory B cells lurk in the bone marrow for future use. Okay, and just in terms of terminology, antibody production is known as, we already kind of talked about it as second line of defense, antibody mediated. It's also known as humoral response. So as we already said, our memory B cells are going to lurk in the bone marrow, where they actually stay in very low numbers for a long period of time, even after the invader is eliminated. And this is why when you get sick with something, okay, that doesn't mutate easily. So let's say you did get chicken pox. Your body made antibodies to fight off chicken pox, and your plasma B cells gave that information to your memory B cells. Okay, be on alert for this pathogen because it may come back again. And what your memory B cells do is they lurk in your bone marrow and they wait for secondary infection. They wait for the second time or third time or fourth time you may be exposed to the chickenpox virus. And then what they do is they wait and they wait and they wait. But then if you get exposed to that pathogen again, your immune system response is super fast because we don't have to go through the whole macrophage and then to the helper T and then to the plasma B and then to the memory B. We don't have to do that anymore. So this is why you don't get sick when you have that secondary exposure, because your body already has the antibodies and it's able to make those, or the memory B cells rather, already have the blueprint for the antibodies and it's able to make those antibodies super quickly before you even get ill. Okay, so that's the beauty of the memory B cells. When we talk about booster shots, sometimes that's what's necessary to make sure that there's enough of that blueprint in your bone marrow to protect you. Okay, so for example, like tetanus, it's recommended that you get a booster shot like every 10 years-ish or so, and that's just to make sure that your memory B cells don't get to super, super low numbers so that they can't fight off infection for you effectively. So our next little group is our killer or our cytotoxic and our suppressor or regulatory T cells. Now listen, in our program of studies, because it is a little bit older, it's killer and suppressor. Okay, but the newer terms are cytotoxic for killer T cells and regulatory for suppressor T cells. Okay, but just so you know, in our program of studies, it still says killer and suppressor. So that's what you can expect to see on exams. So killer T's are kind of what the name implies. Remember, they receive information from those helper T's after the helper T's have given the plasma B cells the antigen information, and then they attach to the invaders and they kill them. And the way they do that is they actually puncture the membrane of the invader cell, because when they do that, the invader pathogen can no longer reproduce because its membrane is damaged. They also kill cancer cells. So these guys are active a lot, looking around for abnormalities and pathogens that the helper T's have alerted them to kill. Suppressor T cells or regulatory T cells kind of do exactly what the name implies. They suppress and regulate the action of the humoral immune system. And think of it this way. Once you've healed and you're no longer sick with the cold or the flu or whatever, you don't want your body to keep making antibodies for something that isn't even present anymore in your system. So you can think of the suppressor T's as kind of that negative feedback mechanism where they kind of tell everybody else to stop. And you can see our little guy here. He's like, stop. Okay, so he's telling our B cells and our T cells to take a check, okay, on the production of the antibodies, because they're no longer needed at that point in time. They also prevent autoimmunity. And remember what autoimmunity is. That's when our body perceives our own tissues as something foreign and will create antibodies to destroy tissues. So things like rheumatoid arthritis that attacks tissues of the joint, for example, okay? So our suppressor T's also help with that. And our last little piece here is, why don't antibiotics work on viruses? So antibiotics are for bacterial infections only, not for viruses. Now, why don't they work on viruses? Well, antibiotics, so when you're sick and you go get antibiotics from the doctor, they disrupt various functions within bacterium like cell membranes, because without cell membranes, bacteria can't reproduce. Now, viruses, on the other hand, remember viruses kind of straddle the living and the non-living. They are not capable of reproducing themselves. And so what they do is they hijack and use organelles of a host cell to reproduce. So they don't have the same internal functions to disrupt like antibiotics do. They're just DNA and RNA fragments, and they actually use the apparatus from other cells rather to actually reproduce and replicate themselves. So they remain unaffected by antibiotics.